molecular orbital theory. Now in this case, here we are talking about the molecular orbital. Now let's see what are the molecular orbitals which we get when the orbitals of the atom, that is 1s orbital, 2s orbital and the 2p orbital of the first atom, that is A atoms, combined with the 1s orbital, 2s orbital and 2p orbital of the B atom, that is the second atom. So if the 1s of A combines with 1s, what will we get? If 1s of 2s of A and the 2s of B combines, then what we get? So this is A atom and this is B atom. So 1s, 2s, in 2p we have 3, that is 2px, 2py and 2pz. In B it is 1s, 2s, 2px, 2py and 2pz. So if 1s orbital of the A atom, 1s orbital of B atoms combine together, then what happen? If 1s is combining, means ultimately I can say 2 orbitals are combining, and if 2 atomic orbitals are combining, then 2 molecular orbital will form, and they are sigma 1s and sigma star 1s. 1s, because here the 1s orbitals are combining. Similarly, if 2s and 2s combines, then what happens? If 2s and 2s is combining, the 2s of first orbital is 2s of second, then it is sigma 2s and then sigma star 2s. If the 2px of the first orbital here combines with 2px of the second orbital, then what happens? Then we get a molecular orbital like sigma 2px and sigma star 2px. If 2py and 2py, then we get sigma 2py, in case of px and py, sigma is not formed, it's a pi. So it is going to be pi to px, and here it is going to be pi star to px. In case of y, if the 2py and 2py is combining, then again I can say that here the pi overlapping takes place. So we get pi py and pi star py. And if the 2pz of the first A atom and the 2pz of the B atoms overlap or combines together, then here we get the here the sigma, that is the axial overlapping takes place. Then the molecular orbital which form is called as sigma 2pz and sigma star 2pz. That is a bonding and anti-bonding. So here I can say overall how many atomic orbital has combined, then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 atomic orbitals are combining, so ultimately here we are getting a 10 molecular orbitals. Now, whatever the electrons we are having in case of atom, those electrons are present in case of in 1s, 2s, 2px, 2py and 2pz. Now I just wanted to transfer these electrons. When atomic orbitals combine together to form a molecular orbital, so whatever the electrons was present in atomic orbital, they shifted to the molecular orbital. So if the electrons are shifting to the molecular orbital, then how the electrons will fill? What will be the order of filling? First electron will fill which molecular orbital and then which? Then here, as the rule says, we are going to follow the same rule for the filling of the electron in molecular orbital also, that is the Aufbau principle or Hund's rule. So according to Aufbau principle, the electron will always fill the molecular orbital which have the lower energy level and then to the higher energy level. So here, out of all I can say out of all molecular orbital, the 1s is having the lowest energy. So the molecular orbital will have the lowest energy compared to the molecular orbitals of all other atomic orbital. So here the 1s, from 1s we have 2 molecular orbital, that is a bonding and anti-bonding. From these two, the bonding will have the lower energy, that is a sigma 1s will have the lowest energy, and then sigma star 1s. Okay, after this we have the molecular orbital which is formed from the 2s, that is sigma 2s and sigma star 2s. So molecular orbital which is formed from the 2s, since the 2s orbital, energy of the 2s orbital is less than the 2p orbitals, that is 2px, 2py and 2pz. So that's why the energy of the molecular orbital's energy will be less than the molecular orbital's energy of the 2px, 2py and 2pz. So here sigma star 1s, the sigma 2s will have the higher energy compared to sigma star 1s and 1s, and sigma from sigma 2s and sigma star 2s, sigma 2s will have the low energy and sigma star 2s will have high energy. After that, we are having a 6 molecular orbital, and all these 6 molecular orbitals are formed from the p orbital, that is 2p. Now in 2p, as we all know that we have 3, that is 2px, 2py and 2pz. Now since these 6 orbitals are from the same atomic orbital, that is 2p orbital, so we are going to arrange, or we are going to compare all 6 orbitals together. So from these 6 orbitals, I just wanted to know which will have the lowest and lower energy and which will have the higher energy. Here in this case, I can at least say that the bonding molecular orbital, the bonding means this and this one, these 3 will have lower energy compared to the anti-bonding, that is the star orbitals. But at the same time, these 3, suppose if these 3 are bonding and they are having a lower energy, but from these 3 also, that is a pi 2px, pi 2py and pi 2pz, which will have the lowest energy and which will have the higher energy. That means I just want to compare pi 2px, pi 2py and sigma 2pz. And once these molecular orbitals are compared, then we are going to compare these 3 anti-bonding molecular orbital. So first let's talk about the bonding molecular orbital, that is pi 2px, pi 2py and pi 2pz. Now see, before formation of a bonding molecular orbital, these are the atomic orbitals which were having the same energy. All 3 are considered as a degenerated orbitals. Degenerated orbitals, that is orbitals with us having a same energy. So initially these orbitals were having a same energy, but then they start bonding with the another atomic orbitals and it forms laterally, it combines laterally, means both of them forms pi bond, while this forms sigma bond. And if it is forming a sigma bond, that means here the pz orbitals are overlapping on the axis. And we had learned that on the axis, the extent of overlapping is more. The bond form is strong, and bond form strong, that is the energy decreases to a higher level. So I can say that since here the attraction is strong, so the energy of this 2pz orbital will be less compared to these 2 pi orbitals. Now, since both of them are forming a pi bonds, pi orbital, that means the overlapping type is the same, so same amount of energy will evolve in both the cases. And if the same amount, initially also the energy was same, during overlapping the same amount of energy is evolved, so now the energy left, or the overall energy is for these 2 orbital is going to be same. So here the energy of 2pz orbital, that is a sigma 2pz, is the lowest because of axial overlapping, and these 2, and the energy of these pi orbital is greater than sigma but equal to each other. So in this case, I can say it's a greater than sigma 2pz, means sigma 2pz, from these 6, the lowest energy is sigma 2pz, then pi 2px and pi 2py, and both will have same energy. Both will have same energy means both are belonging to the same level. Okay, after that, now the 3 are over, that is pi 2px, sigma 2pz and pi py. These 3 are over, now only 3 are left. Star 2px, star 2pz and star 2py. Now we have to compare the anti-bonding. Anti-bonding, higher the repulsion, higher will be the energy. So I just wanted to know in which case the repulsion will be more, in case of sigma or in case of pi. So simply I can say if the attraction is more on a sigma, that is on an axis, if the attraction is more, then repulsion will also be the maximum when the orbitals are approaching to each other on an axis. So on an axis the repulsion is more as well as the attraction is more, so similarly the repulsion is also more when the orbitals are approaching on the axis. That means in case of this sigma, where the 2 orbitals are coming closer on the axis, the repulsion will be more, and if the repulsion is more, that is the energy will increase. While here in case of pi, the repulsion will be less because the orbitals are coming laterally. So from these 3, the anti-bonding, which anti-bonding molecular orbital or where the repulsion is the maximum, sigma, so that sigma will have the highest energy. So in this case I can say 2px and 2py. From this the higher energy will be of pi star 2px and pi star 2py, both will have again the same energy, and from these 2 also the higher energy is sigma 2pz star. So this is the energy level diagram, energy level for the molecular orbital. So whenever the electrons will come, the electron will first fill sigma 1s, then sigma star 1s, then sigma 2s, then electron will fill sigma star 2s, then electron will fill sigma 2pz. Each molecular orbital capacity is of 2 electrons. So everywhere 2 electrons will be filled. After filling sigma 2pz, when the electron will come to these two conditions here, in this case, both have the same energy. And if both have the same energy, then we follow the Hund's rule, according to which if there is a degenerated orbital, that is orbital having the same energy, then electron first fill singly and then pairing. So after filling, when the electron comes here, so here in this case the electron first fills singly both of them, and once they fill singly, then pairing takes place. And then same thing happen here also. First they fill singly and then pairing, and after filling all, sigma 2 star 2pz will be filled. So while to remember this order, just keep in mind that first you have to write the energy order of 1s, and in 1s also the bonding will be low and the anti-bonding will be high, that we know. Then you have to write for 2s, and then you have to write for 2p. In case of 2p, you have to start with the sigma and end with the sigma, that is sigma 2pz, and the end will also be the sigma. In between the pi will come, the pi 2 bonding, 2 anti-bonding, and both will have same energy, and the bonding will have the lower energy compared to the anti-bonding. So this is the order. Now we have, let's represent the same order with the help of molecular orbital energy level diagram. So we have to represent all these orbital in a diagrammatically form. So from, we have to total draw 1, 2, that is total how many levels? 1, 2, 3, 4, 5. These two will come on the same level, that is 6, 7 and 8 levels. Now let's see how it is drawn. That is a molecular orbital energy level diagram. One s orbital of A atom. This is for A atom. Here we have the 1s orbital for B atom. Now when 1s orbital of the A atom will combine with the 1s orbital of the B atom, then ultimately a molecular orbital will form. Molecular orbital, 2 molecular orbital. One will be bonding and the second one will be anti-bonding. The bonding molecular orbital will have the lower energy level, that is bonding, that is sigma 1s, and this is going to be sigma star 1s. Like 1s orbital combined in the same way, I can say that 2s will also combine. So the 2s orbital of the first A atom will overlap with 2s orbital of the second B atom. Now so 2s and 2s is overlapping or combining. So again the 2 more molecular orbital will form. One will be bonding and one will be anti-bonding. Bonding and this is anti-bonding. Bonding, so it is called sigma 2s and this is called sigma star 2s. Then 2p orbitals combine together. In case of 2p, there are each 2p contains 3 orbital, that is px, py and pz. And there are total 6 orbital, but at the same time I can say there are the 4 levels, 1, 2, 3 and 4. So out of 4 level, 2 are bonding and the 2 are anti-bonding. So out of 4, 2 are bonding and 2 are anti-bonding. So 4 levels are okay. So 2p orbital 1, 2 and 3, that is 2px, 2py, 2pz. This is again 1, 2 and 3, 2px, 2py and 2pz. In case of this, by sigma to pz have the lowest energy level. Then the next level, this is pi to px and pi to p. This is sigma to pz, pi to px, pi to py. Here we have pi star to px and then pi star to py, and finally here we have sigma to pz. Sorry, sigma star to pz, anti-bonding. So this is the molecular energy level diagram. Here, when we move from bottom to top, the energy continuously goes on increasing. So this diagram, from this diagram I can say that 1s is having the lowest energy, sigma 1s, then electron, when the electron will fill, first it will fill sigma 1s, then sigma star 1s, then sigma 2s and sigma star 2s. After this, electron will move to sigma to pz. After filling sigma to pz, when the electron will reach to this level, here first electron will fill both singly and then pairing will take place. The same thing here, both have the same energy, so first fill singly and then pairing, and then finally the electron will fill this last orbital. So this is the molecular energy level diagram for the molecules in which the atoms have the atomic number between from 1s to 2p. That means where the electrons are present in 1s, 2s and 2p molecular orbitals. Now, but the same molecular orbital or the same energy level diagram or the same order of energy is not correct in the case of certain molecules, and these molecules are nothing but the boron, that is B2, C2 and N2 molecules. In case of B2, C2 and N2 molecules, this energy level diagram is slightly different. In case of B2, C2 and N2 molecules, this sigma 2pz, pi 2px and pi 2py comes, sigma 2pz, pi 2px and pi 2py comes first, and then sigma 2pz and sigma 2pz comes. Means here in case of B2, C2 and N2 molecule, the energy order is slightly changed. The change is sigma 1s, others are going to be same, star 1s, sigma 2s, sigma star 2s. After this, sigma star 2ps, instead of filling the sigma 2pz, the electron fill pi 2px and pi 2py. And then sigma 2pz is filled. After that, again the energy level is same, that is then pi star 2px equal to pi star 2py, and then finally filled sigma star 2pz. In case of B2, C2 and N2 molecule, the size is small. So in that case, in case of these three, there is a repulsion between the large repulsion between the sigma star 2s and sigma 2pz. And due to that large repulsion, what happens? The sigma star 2s comes down, means due to the repulsion, it moves downside, while sigma 2pz's energy increases and it moves upward side. So ultimately, its level moves, becomes higher than pi 2px and pi 2py energy level. So this is a molecular energy level diagram. Now let's see the certain points which are on which the question can be asked when it is asked, when it comes from the molecular orbital level. But at the same time, keep in mind that for B2, C2 and N2, you have to follow this configuration where sigma 2pz have the higher energy level. That means you have to only change these two energy level. Sigma 2pz, pi 2px and pi 2py. After filling this, electron will move to pi 2px, pi 2py and then sigma 2pz. Okay, now let's see the certain more points which are important for the examination, for the MCQs, I can say. Okay, so the points are, the first one, suppose here we, as I said, whatever the things we are going to write, it is about the molecular orbitals. Here the data, whatever the data we get from this orbital and this orbital, this is about for the atomic orbital. This represent atomic orbital, this represent atomic orbital. But this middle one, whenever the question comes for the molecular orbital, you have to think only about this middle orbital because these orbitals are molecular orbitals. Now, Na is the number of electron in anti-bonding molecular orbital. Anti-bonding molecular orbital, MO, that is a molecular orbital. NB is the number of electron in bonding molecular orbital. Okay, if Na is greater than NB, then I can say molecule is unstable. If Na is less than Nb, then the molecule is said to be stable. And if Na is equal to Nb, then I can say that the molecule does not exist. Suppose if the question is asked on any molecule where Na and Nb I got equal, so if Na and Nb are equal, then I can say that molecule does not exist. Na is greater than Nb. Na is greater than Nb, that means the number of electron in anti-bonding molecular orbital is more than number of electron in bonding molecular orbital. Logically, this is not possible because whenever the electron will fill first the lower energy level. Lower energy level means in all the cases the filling will takes place in case of bonding molecular orbital. And if the electron is first filled in a bonding molecular orbital, then in case of anti-bonding the electrons cannot be more than bondings. That's why it is said that if Na is greater than Nb, that is a molecule is unstable. And if Na is less than Nb, the molecule is stable. According to the rule, that is since the electron first fills bonding molecular orbital. And if both are equal, that is molecule does not exist because between there is a no bond. Let's see from the next formula, we can predict that why I said that Na equal to Nb does not, if any molecule having this condition, then why it does not exist. The next is bond order. The bond order, the formula is Nb minus Na upon 2. What is bond order? Then it's nothing but the number of bond formed between the two atoms. For example, for hydrogen molecule H2, between two hydrogen single bond is formed, so bond order is 1. For O2, between two oxygen atom, 2 bonds are formed, so bond order is 2. For nitrogen, 3 bonds are formed, so bond order is 3. So Nb minus Na upon 2, this tells us about the bond order. So the number of bond formed between the two atoms. Now see, if Na and Nb becomes equal, suppose if Na and Nb is equal to Nb, then I can say bond order will be 0. Bond order is 0 means no bond between the atoms, and if no bond present between the atoms, that means such molecules will not exist. And that's why it is written that if Na is equal to Nb, the molecule does not exist. Then third one, if all molecular orbital then molecule is a diamagnetic. If all molecular orbital have a paired electron means in all the molecular orbital, each molecular orbital have a capacity of 2 electron. And if all orbitals are paired, means if all electrons are paired in a molecular orbital, then it is called as a diamagnetic. We have the substances like paramagnetic and diamagnetic, somewhere related to the magnetic property. The substance which is attracted by the magnetic field, or I can say the substance which have a magnetic property, they are called as a paramagnetic. And the substance which is not attracted by the magnetic field or which is not having a magnetic property is called as a diamagnetic. A substance possesses a magnetic property only if it is having an unpaired electron, and since here all the electrons are paired, so that substance will not have any magnetic property, and such substances are called diamagnetic. And so as I said, if there is a unpaired electrons are required for having a magnetic property, and so the substance is going to be a paramagnetic. So if any molecular orbital have unpaired electron, then molecule is paramagnetic. So the molecule, with the help of molecular orbital theory or with the help of filling of the electron in this energy level, we can decide whether the given molecule is a diamagnetic, paramagnetic, paramagnetic or diamagnetic. If the molecular orbital have an unpaired electron, it is going to be a paramagnetic, and if all the electrons are paired, then it is going to be diamagnetic. And there is one more type that is called as a ferromagnetic. The ferromagnetic, that is a substances which is having a strong paramagnetic property, means strongly attracted by the magnetic field, and that cannot be explained on the basis of this. So here we just differentiate whether the molecule is attracted by the magnet or it is not. If it is attracted, para. If it is not, then it is a diamagnetic. Now here let us arrange the Now let's use all the theory or all the things which we studied for in molecular orbital theory in a hydrogen molecule. Here we have to draw the energy level diagram for the hydrogen molecule, and plus let us calculate the bond order, whether it is a paramagnetic or diamagnetic, all the details for H2 molecule. Now H2 molecule is formed from the hydrogen atom, and if it is forming from the hydrogen atom, then I can say hydrogen whose atomic number is 1, its electronic configuration is going to be 1s1. 1s1 means it have electron only in 1s orbital. So in case of H2 molecule, I can say hydrogen have 1 electron, so H2 will have total 2 electrons. And H2 have 2 electrons, so its electronic configuration is going to be. So electronic configuration of H2 molecule is nothing but here in case of H2 molecule there is only 2 electron, and if it have 2 electron, then both the electron will move to the first orbital, and first orbital is nothing but the sigma 1s. So electronic configuration for H2 is going to be sigma 1s with 2 electron. Every molecular orbital's capacity is of 2 electrons, so both the electrons will get occupied in sigma 1s. Now I just wanted to draw its molecular energy diagram. So molecular energy diagram for H2 molecule will be, it will be something like this: 1s orbital of first hydrogen and 1s orbital of the second hydrogen atom. 1s orbital of first hydrogen will also have 1 electron, second will also have 1 electron. Both are combining, so they both will form a 2 molecular orbital. One will have low energy, one will have high energy. This will be sigma 1s and this will be sigma star 1s. Total electron in H2 molecule is 1 plus 1, that is 2. So if there is a 2 electron, so these electrons will transfer to the, initially the electron was present in atomic orbital, but after the formation of the molecular orbital, these electrons will shifted to molecular orbital. 2 electron. The first electron will fill to the lower energy level, that is sigma 1s, bonding molecular orbital, have 2 capacities, so both the electrons will get accumulated in this. That means sigma star 1s will remain empty. No electrons will enter in sigma star 1s. So here I can say this is the molecular energy level diagram for the hydrogen molecule. This gives the data for the hydrogen atom, this gives the data for hydrogen atom, while this middle one is for H2 molecule. Okay. Now I just wanted to know the bond order for H2 molecule. So for bond order, as I said, we have a formula. Bond order, the formula is Nb minus Na upon 2. And Nb minus Na upon 2, so the electron in a bonding molecular orbital. Electron in bonding molecular orbital, here we have 2 electron in a bonding molecular orbital, and no electron in anti-bonding. Anti-bonding is empty, and upon 2, that is equal to 2 upon 2, that is 1. So I can say that in the hydrogen molecule, 2 hydrogen atoms are bonded by a single bond. So here the bond order is 1. Whether it is a paramagnetic or diamagnetic, the many time it is question, it is asked in the MCQs, H2 is a paramagnetic or diamagnetic, or O2 is a paramagnetic or diamagnetic. What will be the bond order for O2 and like that? From molecular orbital theory, the majority of many times in an exam, the questions are asked from the molecular orbital theory only. So here for the O2 molecule, for the H2 molecule, whether it is a paramagnetic or diamagnetic, from electronic configuration we can say that, see, for answering all the MCQs question, there is no need of drawing this molecular orbital diagram. From this, from the electronic configuration only we can predict the answers. Now it's a sigma 1s2, 2 electrons are there, maximum capacity 2 means, and the 2 electrons are there, that means electrons are paired. And the same thing we can observe in case of diagram also. The question is whether the molecule is paramagnetic or not, or diamagnetic or not. So we are going to concentrate on the molecular orbital, not on the atomic orbital. So molecular orbital only 2, and there is only 1 electron molecular orbital is filled, and that to have pair electron. And pair electron, that means it is a diamagnetic. So H2 is a diamagnetic in nature. So here we can say H2 is a diamagnetic in nature. So here the molecule or ions, bond order, paramagnetic nature, magnetic behavior, or okay. The we did for H2 molecule. So H2 molecule, bond order I got 1. Paramagnetic or diamagnetic, I can say it's a diamagnetic. So for diamagnetic, I'm just writing D. D stands for the diamagnetic. Suppose if the question is asked for H2 plus ion, H2 plus ion, that is H2 is carrying plus charge now. So H2 is carrying plus 1 charge, so H2 total electron is 2, but since it carry plus 1 charge, so 1 electron is less, that means it have now only 1 electron. So electronic configuration for H2 plus will be, electronic configuration in H2 plus there is only 1 electron, so the configuration will become sigma 1s1. And sigma 1s1 H2 have only 1 electron. 1 electron means only this will filled, 1 will remain empty. And sigma 1s1, that means here the bond order, if I am calculating, then bond order will be equal to Nb minus Na, Nb that is 2 electron, Nb that is in bonding there is only 1 electron, anti-bonding 0, that is upon 2. So I can say that the bond order is half. And diamagnetic or paramagnetic, then simply since there is only one orbital which is completely filled and that to have only 1 electron, so it is going to be a paramagnetic in nature, unpaired electrons, so paramagnetic. So if the question is on H2 plus, it is an ion, then bond order is 1 by 2 and it is a paramagnetic in nature because unpaired electron is there. So paramagnetic. Suppose if the question, if it is He2 molecule, what will happen in case of He2 molecule? So He2 molecule, H2 will become He2 now. He2, He whose atomic number is 2, I can say, so its electronic configuration is going to be 1s2. 1s2, that means S is having 2 electron. So He2, total electron in He2 will be 4. Each He is having 2 electrons, so it will be a 4. Electronic configuration, if I am writing for He2, so electronic configuration of He2 will be equal to, the first 4 electrons are there. First we have sigma 1s, will have 2 electron. After sigma 1s, what is the next energy? It's a sigma star 1s. So sigma star 1s, it is 2. So total 4 electrons, 4 are occupied. The same thing we can represent in diagram also. 1s, 2 electron, and here also 1s, 2 electron. Sigma 1s 2 and sigma star 1s 2. Total 4 electrons. So 2 will filled in this case and 2 will be here. So now it is He2 molecule. Now let us calculate the bond order and the whether it is a diamagnetic or paramagnetic. Bond order, Nb minus Na, the number of bonding orbital is 2, anti-bonding is also 2, so 2 minus 2 is 0 upon 2 is 0. So I can say if it is a He molecule, then between He molecule there is a 0 bond, means no bond. And if no bond, that means such molecule does not exist. He2 will not exist only, right? So He2 molecule does not exist because the bond order is 0. So if I have He2 molecule, then its a bond order is 0, and if the molecule does not exist, then there is no need of writing whether it is a paramagnetic or diamagnetic. Suppose if the molecule exists, and then here the answer was a diamagnetic because electron was paired in a molecular orbital. But since the molecule does not exist, so no need of writing whether it is a paramagnetic or diamagnetic. Then next molecule is lithium, Li2 molecules. The next is the Li2 molecule, that is a lithium molecule. Now what happens in case of lithium molecule? The lithium molecule which is formed from the lithium atom, the lithium whose atomic number is 3. So its configuration is going to be 1s2 and 2s1. 1s2, 2s1, since now we all know that the electrons which are present in outermost shell, only they takes part in the bond formation. So here the electron present in a 1s orbital will not form a bond, only the electron present in a 2s orbital will form a bond. So here this 1s electron will be called as a non-bonding electron because it doesn't take part in a bonding. So we have only 2s1 configuration, that is only electron present in 2s will take part in a bonding. But overall the lithium is having a 3 electrons, so Li2 molecules, I can say that it will have a 6 electron. And if Li2 is having a 6 electron, then what will be its configuration? So electronic configuration is going to be, it is sigma 1s 2, sigma star 1s 2, and then we will have 2 more electrons are left. So now the electron will shift it to, after 1s, star 1s, now the electron will shift it to sigma 2s also. So it's sigma 2s2. Now in the case of this Li2 molecule, first shell is already completely filled. 1s means first shell only have only one orbital, that is s orbital. So here I can say that 1s first shell is completely filled. So instead of writing sigma 1s and sigma star 1s, in a configuration I can also write kk, the k that is a first shell. So first k is for the bonding and the second k is for anti-bonding, and then left is a sigma 2s. So if the kk is written, that means it indirectly it represents the sigma 1s and sigma star 1s, that too filled orbital. Okay, so how to draw its energy level diagram for this molecule? So for drawing the energy level diagram, 1s orbital, now it becomes non-bonding, it will not take part in a bond formation. So 1s orbital, as I said, it is a non-bonding now. Then electron is moving to the 2s orbital. 2s orbital, 1s is completely filled, that is a 2 electron in 1s orbital. Electron is moving to 2s orbital. Two s1, here also 2s, and we have 1 electron. Now 2s, 2s, 2 orbitals are combining, so 2 new orbital will form sigma 2s, that is bonding and anti-bonding. So sigma 2s, and this is going to be a sigma star 2s. So total in case of this 2s, 2s, 2 orbitals, and the electron is 1 plus 1, that is the 2 electrons are there. So these 2 electrons will now get shifted to this bonding molecular orbital or anti-bonding. 2 electrons, so they will shift it to bonding only. And if it is shifted to only bonding molecular orbital, means I can say in case of lithium molecule, again, what is the bond order? So for lithium molecule, I can say that bond order is, for lithium molecule, the bond order is, the formula is same, Nb minus Na upon 2, bonding. Now in case of 1s and this, here we have star 1s, sigma 1s and sigma star 1s, so already they are nullifying each other. So if I will consider these two, then the things will be okay, or we cannot consider. The bonding bonds are bond order which measures the bond formed between the atom, and the bonds are formed only by the electron which is present in outermost shell, that is this one. So for calculating a bond order, we will consider only these orbitals which are taking part in a bonding. So Nb, that is a bonding electron, there is only 2 bonding electron, minus anti-bonding electron. Anti-bonding, there is no electron in the anti-bonding. So 2 minus 0 upon 2, again I can say that bond order is 1. So in case of lithium molecule, the 2 lithium atoms are bonded by single bond. And that 2 extra electron, that single bond is because of the contribution of the sigma 2s orbital, and hence since the sigma 2s orbital is having these 2 electrons, that's why the bond is a sigma bond. Now in case of Li2, the bond order is 1, and whether it is a paramagnetic, diamagnetic, then I can say there is only 2, this molecular orbital is having a pair, there is no orbital having a unpaired electron, all are paired, and all are paired, that means I can say it is a diamagnetic. Lithium, after lithium molecule, the next we are having a beryllium molecule. Beryllium, whose atomic number is 4, and being a 4, its a configuration will changes to from 1s2 to 2s1, it will become 1s2, 2s2. So S have now 2 electrons, and if S have 2 electrons, then its a configuration will changes to sigma 1s2, sigma star 1s2, sigma 2s2, and sigma star 2s2. So total 4 electrons, this will be the configuration. Now let's see the diagram, molecular orbital diagram for Be2 molecule. So for Be2 molecule, total 4 electron in beryllium atom, so total electrons will be 8, 2, 2, 4, 2, 6 plus 2, 8. 4 electrons, 1s, 1s2, now here it is 2s also have 2 electrons. So 4 electrons, 2 will be in bonding and 2 will be in anti-bonding. So bond order now for this, bond order will be 2 minus, anti-bonding also have 2 electrons. So 2 minus 2, that is 0. So 0 upon 2 is 0. So beryllium, I can say in case of beryllium, there is a no bond exists between the two beryllium atom as the bond order is 0. So Be2 molecule bond order is 0 and hence it does not exist. And if it does not exist, then there is no need of writing whether it is a paramagnetic or diamagnetic. Then after beryllium, the next is boron molecule. Boron, whose atomic number is 5, and atomic number is 5, then its electronic configuration is 1s2, 2s2 to p1. After s, now the p orbital also comes in the picture, that is 2s and 2p have 1 electron. Now in the case of this configuration, this is from the first shell and these two, both of them are from the second shell, that is principal quantum number is 2. So all three electrons will take part in a bonding, that is from 2s as well as from 2p. So after 2s, now let us draw the energy level diagram for 2p. We have total 4 level. To px, to py, to pz, and the same thing here also, to px, to py, and to pz. This is present in 2p1, that is only 1 electron in the p orbital. In case of B2, C2 and N2 molecule, I said the order is slightly different. The sigma 2pz, instead of sigma 2pz, the pi 2px and pi 2py have the lower energy. So pi 2px and pi 2py. And here it will be sigma 2pz. And the remaining order is same, that is pi star to px, pi star to py, and finally the last is sigma star to pz. Okay, now in case of boron, there is a 1 electron in this and 1 electron here. So 2 electron, now both the electron will get shifted to the molecular orbital. So for molecular, when they will shift it to molecular orbital, 2 electron we have to fill. Both have the same energy level, and since they have same energy level, so first they will fill singly. Now I want to write the bond order for the boron molecule, that is B2 molecule. So it's a bond order. Before that, what will be its configuration? So it's a configuration for boron is going to be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. After this sigma star 2s2, I am writing here, it is going to be after sigma star 2s2, it is pi 2px 1 and pi 2py 1. Again, after sigma star 2s, I know that the pi 2px is equal to pi 2py comes, and since both have the same energy level, so first they will fill singly and then pairing will take place. Now for boron molecule, what will be the bond order? Bond order, I can say it is 2 plus 2, that is total 4 bonding molecular electron in a bonding orbital, minus anti-bonding is only this one, that is minus 2. So 4 minus 2 upon 2, that is 2 upon 2. So answer is 1. So bond order is 1. Now this, in case of boron molecule, 2 boron atoms are bonded by the single bond. Bond order is 1. I just wanted to know whether it is a sigma bond or pi bond. The rule says that the first bond is always a sigma bond, but in the case of this boron molecule, I can say that these 2 extra electron which we are getting, that 2 extra electron is from these pi orbital, means these 2 extra electrons are the part of pi orbital, and hence the bond is going to be a pi bond. Out of 4 electrons, 2 was out of 4 bonding or electrons. There is a 4 bonding or electrons and 2 anti-bonding, and these 2 anti-bonding electrons will nullify these 2 bonding electrons, and so that extra 2 electrons are left. So whatever the extra 2 electrons we are getting, because of which one bond is formed, since it is a part of a pi orbital, that's why the bond is going to be a pi bond between the 2 boron atom. So in case of boron molecule, B2 molecule, the bond order I got 1, Whether it is a paramagnetic or diamagnetic, the diagram says that, or the configuration says that there is a single electron in a molecular orbital, and if there is a single electron in a molecular orbital, it is going to be a paramagnetic in nature. After boron molecule, the next we have C2. In case of carbon molecule, if it is a carbon, atomic number is 6 and it becomes 2p2. And 2p2, that is carbon-carbon total electron, 6, that is a total 12 electrons. So 2, 2, 4, 2, 6, 2, 8, 4 electrons are left. First they will fill singly and then still 2 electrons are left. So pairing will take place. Now in the case of this, 2p is having 2 electron. So now total 4 electrons are there in case of carbon which can be filled. So 4 electrons, so first these two will fill singly and then pairing. So in case of carbon, what will be the bond order for carbon? For carbon, I can say the bonding electron 2 plus 2 plus 2, that is 6, minus anti-bonding is 2 upon 2, that is I can say 4 upon 2, that is 2 bonds are formed. That is in carbon, the 2 bonds are formed. The carbon-carbon means in C2 molecule, 2 carbon atoms are bonded by the double bond. Now with generally the double bond, if there is a double bond between the two atoms, then we say that there is one is going to be a sigma bond and one is going to be a pi bond. Now let's see what happens in case of carbon molecule. Again, out of 6 bonding electron, 2 electrons are subtracted, and that 2 electron was from this sigma star 2s, means I can say sigma electron and these sigma electrons, they are nullifying each other. So extra 4 electrons which are forming a 2 bond, that 4 electrons comes from these two. And if that 4 electrons comes from these two, that means both the bonds are going to be a pi bond. So in case of C2 molecule, bond order is 2 and it is magnetic or electrons are paired, so I can say that it is a diamagnetic in nature. Suppose if there is a C2 plus ion, if it is a C2 plus ion, then what will happen? If there is a C2 plus ion, then I can say total electron in carbon is a 12, but if it is a C2 plus, that means 1 electron is lost. So instead of 12, there will be only 11 electrons. So configuration will be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2px and sigma 2py. 2, 2, 4, 2, 8 plus 2 is 10. And then only 1 electron is left. That means this will be unpaired. So C2 plus will have 1 electron less. That means there will be, this electron will not be there. And 1 electron less, it means what will be the bond order then? Then instead of having a 6 electron in a bonding molecular orbital, 1 is less. So now we will have 5 minus 2 upon 2. That means it will be a 3 upon 2. And 3 upon 2, that means the bond order is going to be 1.5. And since this electron will get unpaired, as I said, there will be only 1 electron. Unpaired, that means it is going to be a paramagnetic in nature. Okay, after that, suppose we have the next molecule. After carbon, the next is nitrogen molecule, N2. Now what will happen in case of N2? N2 nitrogen having the configuration 1s2, 2s2, 2p3, that is this electron is also filled. And in case of nitrogen, N2 molecule, there is a total 14 electrons. So let us write the electronic configuration. For N2, sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. After this, till here it is a 12 electrons. So 2 more electrons are added. So its a configuration will change after pi to py. We have sigma. So sigma to pz2. So 3 electron, that is total 6. So out of 6, 2 will be here, 2 will be here, and the left 2 are here. So in case of nitrogen, the bond order is, here, total bonding electron is 2 plus 2 plus, that is 8, 8 minus 2 upon 2, that is I can say 6 upon 2, that is equal to 3. So bond order is a 3. Now that 3 bond order, we can say that here these 3 pair of electrons comes from these 3 and these 3, that means 1 bond is going to be a sigma in case of nitrogen triple bond. So 1 is going to be a sigma and 2 is going to be a pi. Diamagnetic or paramagnetic, I can say that all electrons are appearing paired, so it is going to be a diamagnetic. So nitrogen molecule, bond order is 3 and this is C2 plus. And so that it is going to be a diamagnetic. Okay. After nitrogen molecule, the next is a O2 molecule. O2 molecule, each oxygen atom is having a 6 electron in the each oxygen atom. Now for oxygen atom, it is going to be a 1s2, 2s2, 2p4. And if it is 2p4, that means here it is 2 and 1 more electrons will be added. But in case of oxygen, I can say that there is a total 16 electrons. And if it is a 16 electrons, okay, before oxygen, let us calculate for nitrogen minus, N2 minus. What will be the bond order, or whether it is going to be paramagnetic or diamagnetic if it is a N2 minus. N2 minus, that means it will have 15 electrons overall. 15 electrons, still here we have 14, and if it is a 15, then configuration will changes to 1s2, star 1s2, sigma s2. Here it is 14, one more electron is there. That means that one more electron will shift to after sigma to pz, what comes pi to px and pi star to px and pi star to py. So that one electron will shift it to pi star to px, means here. And if one electron is shifting to this, it means it will be a paramagnetic because single electron will be there. And in case of N2 minus, here we are writing for N2 minus, paramagnetic, plus bond order will be like 2, 2 to 8, 8 minus anti-bonding. Now there is a one more anti-bonding electron. So 2 minus 1, that is a 3. So 8 minus 3, that is 5 upon 2. So bond order is going to be 2.5. Now let's see for O2. As I said, there is a 16 electron. But for the oxygen molecule, we have that original energy level. For, as I said, for B2, C2 and N2 molecule, the energy level was changed. Okay, so for oxygen now we have the original energy level. So let us see. So first, we have the energy level, original energy level where we have the pi sigma to pz as a lower energy, and the pi to px and pi to py have higher energy level. The next is a O2 molecule. So O2 molecule, oxygen atomic number is 8. So its configuration is going to be for oxygen atomic number 1, 8, that is 1s2, 2s2 and 2p4. So 2p have 2s have 2 electron and 2p have 4 electrons. And as I saw, O2 molecule will have overall 16 electrons. So 16 electrons, so what will be its configuration? Configuration will be sigma 1s2, sigma star 1s2, then sigma 2s2, sigma star 2s2. After sigma star 2s, for B2, C2 and N2 molecule, the pi to px and pi to py was written first and then sigma to pz. But in case of this O2 molecule, the actual energy level comes, and the actual energy level, after sigma star 2s, the electron moves to sigma to pz. So sigma to pz2, how many electrons? 2, 4, 6, 8, 10, 12. Then pi to px and pi to py will come. Both have same energy. That's why the first electron fill them singly and then pairing takes place. So 2, 2 electron. 2, 4, 6, 8, 10, 12, 14. Still 2 electrons are left. And these 2 electrons will move to the next energy level. After pi to px and pi to py, the next energy level is a pi star to px and the pi star to py. So pi star to px and pi star to py, again they have the same energy. So first the electron will fill them again singly, that is pi star to px plus 1 and then pi star to py, one more electron. So I can say that in case of O2, there is an unpaired electron. From this I can say there is an unpaired electron. That means it is going to be paramagnetic. Now in case of O2, what will be the bond order? For bond order, I can say forget about these 4 electrons because they are nullifying each other. 2 minus 2, 2 minus 2, 2 minus 2. Just count these 2. 2 plus 2 plus 2, that is 6. 6 minus 2. 6 minus 2 is 4. 4, that is 6 bonding electron minus 2 anti-bonding. So 6 minus 2, 4. 4 upon 6 minus 2, 4. 4 upon 2 is 2. That is a double bond will form. That is bond order is 2. Now in case of this, as I said, it is 2p and 2p. Sigma to pz will come first, and then pi to px and pi to py. Sigma to pz, 2 electrons, 2 electrons, 2 electrons, and then it's a 2p4. So still 2 electrons are left. So 1 electron here and the 1 electron in this case. So in case of O2 molecule, as I said, bond order. So bond order is 2 plus 2 plus 2. While if I am writing through the electronic configuration, better not to consider this one. But if I am considering this, you can consider this electron or not also for calculating bond order. So suppose if I am considering these two, this 2s orbital also. So 2 plus 2 plus 2, that is 8 electrons minus 4 anti-bonding, that is 4 upon 2. That is equal to 2. Now in case of oxygen molecule, the bond which is formed, it is double bond, and out of those two double bond, one bond is a sigma and one bond is a pi. Because these two are nullifying, remaining 6, out of these 6, the 2 pi electrons are cancelled. So out of 6, 2 pi electrons are cancelled. So we are getting a 2 pair of electron, 4 electron, that is 2 pair, then one is sigma and the one is pi. So O2 molecule, we have the bond order is 2, and it is a paramagnetic or diamagnetic, then I can say that it is a paramagnetic because electrons are unpaired. Now suppose if the question is O2 plus. O2 plus means the total electron is going to be only 15. 15 electron, that means the configuration will be 1 electron less, so configuration will be only up to here, sigma pi star to px1. That means one anti-bonding electron has been reduced, and if one anti-bonding has been reduced, then how many, what will be the bond order? 2 plus 2 plus 2, 6, 6 minus 1, that is 5, 5 upon 2, 2.5. So bond order is going to be 2.5 in the case of O2 plus. Bond order will be 2.5. Paramagnetic or diamagnetic? Paramagnetic, because it will be a 2px1. If it is a O2 minus, then there will be 16 electrons. 16 means one more electron, then 17 electrons. Then this will get paired. That means anti-bonding electron will increase, and if anti-bonding electron is increasing, then bond order will reduce to 1.5, because it will become 8 minus anti-bonding will become 5. So 3 upon 2, that is 1.5. And again it is going to be paramagnetic in case of O2 minus. If it is a fluorine molecule, F2, if it is F2, then 2p5, that means one more will get paired. It will become, that is 1 fluorine. Total electrons in a fluorine will be 9 plus 9, that is 18. So this will also get paired. So 2p5, 2 more electrons are added, so here and here. So I can say that the bond order is going to be 8 minus 6 upon 2, that is 2 upon 2, that is 1. So in case of fluorine molecule, the bond order is 1. Paramagnetic or diamagnetic, the diagram says that it's a diamagnetic. The next one, if I am considering Ne2 molecule, that is neon molecule. In case of neon molecule, it will be a 2p6. This will also fill. That means the number of bonding and anti-bonding will become equal. And if the number of bonding and anti-bonding becomes equal, 8 minus 8 will be 0. That means no bond. And since the neon is a noble gas, so two neon molecule atoms will not combine. And hence I can say the molecule does not exist and bond order will be 0. And if does not exist, then there is no need of writing whether it is a paramagnetic or diamagnetic. So these are the molecular orbital diagram for the molecule from hydrogen to neon, and how to write their electronic configuration, and how to calculate their bond order, and how to decide whether the given substance is a paramagnetic or diamagnetic.